Hi, my name is James Walker, and I'm going to talk to you about my work with reaction wheel momentum control while electrostatically tugging space objects. And I just want to acknowledge my co-authors, Kaylee Champion and Dr. Hans-Peter Schaub. So space isn't empty. It's actually full of energetic plasma that interacts with spacecraft and causes it to charge. And this spacecraft charging can be caused by a variety of mechanisms, some of which are shown here. But they will cause negative currents and positive currents on the spacecraft, which the balance of these currents ends up resulting in the electrostatic potential of the space object deviating from that of the environmental plasma. And this work is mainly concerned with geostationary and cislunar orbits, where the electrostatic potential of a spacecraft can reach tens of kilovolts. And with electrostatic potentials, with these large electrostatic potentials, you can actually get some interesting behavior with close proximity spacecraft. Specifically, spacecraft in close proximity to each other will generate electrostatic forces and torques on each other. And when you have large electrostatic potentials, you'll get large perturbations that affect the spacecraft motion. And while this can be an issue for some missions, it actually offers a unique capability in terms of debris removal. So the electrostatic tractor is a method for large debris removal from geostationary space that actually utilizes these electrostatic forces and torques. So the idea is you have a servicing spacecraft equipped with a high energy electron gun. It directs the electron gun at the debris object. This increase in negative current on the debris will cause it to charge negative, while the expulsion of the negative particles from the servicer will cause it to charge positive. With these opposing charges, an attractive force is created between the two spacecraft, which allows the servicer to actually manipulate the motion of the debris object and tug it to a graveyard orbit, which is no longer a threat to geostationary spacecraft. Now, when spacecraft are operating in close proximity to each other and have these really large electrostatic potentials, they're going to experience large electrostatic torques. And for operations such as the electrostatic tractor, where it takes a couple months to uh, reorbit a multi-ton object, this servicer is going to be experiencing electrostatic torques continuously throughout the mission. And the reaction wheels of the servicer is going to have to store this increase in angular momentum in order to continually maintain its desired attitude. Well, over the course of that long duration of time, you're going to have to implement methods for managing the angular momentum of a servicer, specifically because the reaction wheels of the servicer will spin up, and if they get too fast, they'll saturate. So you have to be able to find a way to reduce these wheel speeds. And so traditional methods for this include using thrusters or magnetorquers to apply this external torque to manage momentum. However, thrusters do require additional fuel, and magnetorquers are most effective in low altitude orbits, and we are mainly concerned with geostationary and cislunar orbits. So rather than employing these methods, we want to explore the use of actually using electrostatic torques to spin down the servicer's reaction wheels. And we can do this by exploiting the attitude dependence of these electrostatic torques. So if you have an initial servicing attitude that you want to maintain, you're going to experience a torque, cause reaction wheels to spin up. But if you can adjust this attitude to where it now experiences torque that is opposite that at the servicing attitude, you can rotate between these two attitudes to actually manage a spacecraft's momentum. So an idea shown here, you were maintaining a servicing attitude, your reaction wheel reached a point before saturation that you wanted to spin them down. So you rotate to this anti-torque attitude where the reaction wheels are able to spin down. Once they spin down, the spacecraft rotates back to its initial servicing attitude and continues its operations. And we do this by exploiting the fact that the rate of change of the angular momentum of a spacecraft is equal to the external torque that it experiences. So at the servicing attitude, if we experience a positive torque, if we're able to find another attitude that experiences a negative torque, we can rotate between these two and actually keep the angular momentum from continually increasing. So starting with a servicing attitude shown here, you experience an electrostatic torque. If we're able to find this anti-torque attitude, where the torque is actually opposite, rotating between these two attitudes would allow us to manage electrostatic momentum. Now, the key there is we have to be able to find this anti-torque attitude. And the way we do that here is we develop the database of a significant number of relative orientations between the surfacer and the target, and computed the electrostatic torque at each of these attitudes. Now, the idea then is you have a servicing attitude that experiences electrostatic torque. You search the database for the torque that is most anti-parallel to that of at the servicing attitude. The attitude that this torque occurs at is then the anti-torque attitude. This project uses MRP attitude control. Specifically, we use a nonlinear PD reaction wheel motor torque controller. And so that's going to depend on the attitude error of our spacecraft, the angular velocity error, as well as this G matrix, which consists of the spin axes of the reaction wheels. In this case, we're using 3 reaction wheels that are aligned with the principal axis of the spacecraft. It's also going to depend on the reaction wheel speeds and the external torque. In this case, it will be the electrostatic torque. And then finally, we have to use electrostatic force and torque modeling in our dynamics program so that we can actually, compute these electrostatic forces and torques at a given attitude. And we do this by using the multi-sphere method, which is a technique that has been used in multiple papers to include electrostatic forces and torques in dynamics modeling. The idea is to discretize the spacecraft as a collection of spheres, and knowing the voltage of each of the spheres, which, because it's a conducting spacecraft, we're assuming it's going to just be the voltage of the entire spacecraft, we can compute the charge on each sphere. Knowing the charge on each sphere, we can compute the torque that each sphere experiences. And then the net torque experienced by the spacecraft is going to be the sum of all the torques of the spheres. The electrostatic force of the spacecraft is computed in a similar manner, but we are only considering rotational dynamics here and not translational dynamics. So let's look at some results. We have a single momentum maneuver, which consists of, we have a spacecraft with initial angular momentum vector that is large. The reaction wheels are reaching points to where they're starting to become concerned about saturating based on wheel speeds. So it has to have some way of reducing these wheel speeds and managing its momentum. So the idea is it will determine the attitude that offers the most anti-parallel torque to its angular momentum vector, achieve that attitude, and then approach this inertially fixed target, at which point it will maintain this attitude while it transfers its angular momentum to that of the target. And you can see the plot on the bottom left, the red arrow indicates the angular momentum vector, while the blue is the electrostatic torque vector. And if you look at the plots, the plots on the right, you can see the reaction wheel velocities all reach 0 at about the same point. And this is also reflected in the angular momentum plot, where you can see that at about 54,000 seconds, you reach a near 0 angular momentum. Now, this is a very idealized scenario where the angular momentum vector and the electrostatic torque vector are exactly anti-parallel. Their dot product is -1, so they're exactly opposite each other. So we get this very idealized behavior. Now, if we look at a less idealized scenario where the dot product is -0.95, so the torque and the angular momentum are not exactly anti-parallel, we get more realistic behavior. And you can see that with the progression of the angular momentum, where it does decrease as we maintain this attitude. However, the angular momentum does not decrease to 0. It ends up reaching a minimum of about 100 Newton meter seconds at 33,000 seconds, at which point the angular momentum then becomes increasing. And with this more realistic scenario, you can see that we don't achieve a 0 angular momentum, but we are still able to significantly decrease the angular momentum of our spacecraft. So we are getting the behavior that we want. Now let's look at a continuous momentum maneuver. So here we have a servicing spacecraft that is maintaining a desired attitude relative to the target. Well, it maintains this attitude, it experiences electrostatic torques. Once the reaction wheel speeds reach a certain threshold, it rotates to the anti-parallel attitude, the anti-parallel torque attitude, where the reaction wheels are allowed to spin down. Once they reach another threshold, it rotates back to the servicing attitude where its operations are continued. So if we take a look at this video, we have the surfacer maintaining its desired attitude once the reaction wheels reach the threshold. it will increase the separation distance between the two spacecraft, perform its rotation maneuver to the anti-torque attitude. Once it achieves that attitude, it'll decrease the separation distance back down to the nominal 15 meters, maintain this attitude while the reaction will spin down. Once they reach the second threshold, it will increase the separation distance again, perform the maneuver back to the servicing attitude, and then continue the servicing that the spacecraft was doing. And if we look at the reaction wheel velocities, you can see that the threshold chosen here is 50 radians per second, and it is the y-axis reaction wheel that achieves it first. We choose a threshold of 50 radians per second, and then we choose a saturation limit of 100 radians per second. And we keep the threshold relatively low because you'll see that during the maneuvers, the reaction wheel speeds actually exceed the 50-volt threshold, but are still below the 100 radians per second threshold. And if we look at the angular momentum, you can see that the dashed line there indicates the end of the first maneuver. So we are able to decrease the angular momentum of the spacecraft from 60 Newton meters seconds to about 10 over the course of one maneuver. So we are able to significantly reduce the angular momentum of the spacecraft. However, you can also see this clear increasing trend of the angular momentum, and this is a product of the fact that the two torques are not exactly anti-parallel, so you will have angular momentum buildup in the perpendicular component, which results in this continually increasing angular momentum that we cannot account for. So eventually we will reach a point where we can no longer leverage the effect of the electrostatic torques, and we will have to resort back to more conventional methods, such as thrusters. But we can still see that we are getting desired behavior, and we are able to transfer momentum continuously throughout a mission. So this was some preliminary results related to this work. There are a few strong assumptions that we will have to address and remove in future work. The first thing we want to look at is we want to track the behavior of the target, because electrostatic torques are internal torques relative to the two spacecraft systems. So the net torque of the system should not be increasing. Additionally, we want to include translational dynamics and see how this affects our maneuvers. We also want to remove the stationary target constraint, because the motivation for this is specifically related to the electrostatic tractor, where we are working with an uncontrolled debris object. So we want to see how allowing the space debris to rotate affects the overall behavior. And then finally, we want to remove translation behaviors and achieve something more similar to the very first video we showed. I want to acknowledge the funding for this project was through the DoD, through the ND-Sec Fellowship, as well as AFOSR for general support that has enabled electrostatic tractor research. So with that, if you have any questions, feel free to reach out.